Cancer is a complex and deadly disease designed to destroy somebody physically and mentally. Among the many types of cancers, breast cancer and prostate cancer are the most commonly diagnosed among women and men. When these two cancers advance in stage, they become metastatic, and this means that they travel from a primary location to a secondary location, most likely bone. This is known as bone metastasis. When this occurs, the survival rates drop precipitously. We need accurate, complex in vitro models to mimic this condition so that new and robust therapies, effective therapies, can be developed. Here in the Center of Engineered Cancer Testbeds, we have developed a unique scaffold system created from hydroxyapatite and clay and modified with unnatural amino acids. We hope we have developed a material system that is tunable and mechanically and biologically relevant to the bone microenvironment.
So to understand the mechanical behavior of the scaffolds modified with the different unnatural amino acids, we first used the computational approach where we built the atomistic models for the clay and different amino acids and carried out the molecular dynamic studies. Here we observed the non-bonded interaction is higher for butyric acid and clay, which is resulted in higher mechanical properties for the scaffold. At the same time, we observed the increasing despacing for the clay models modified with the different amino acids, so which is dependent on the length of the hydrocarbon chain and the functional groups in the amino acids. To validate these results, we prepared the modified clay with different amino acids and performed the XRD and FTIR studies, where we observed the increasing despacing for the modified clay, and in FTIR analysis we see that the presence of CH and CO vibration band, which confirms the intercalation of amino acid inside the clay sheets. Then we use this modified clay to prepare the biopolymer scaffolds with polycaprolactone and hydroxyapatite. Then for prepared scaffold, we check the microstructure using SEM imaging, where we observe all the scaffolds are porous and the pore size varies from 300 microns to submicrons, even though we didn't observe a significant change in microstructure. Then we use the scaffolds to check the mechanical properties using compression test, where we observe higher compression strength for the scaffolds modified with the butyric acid followed by the pamelic and valeric acid. So here, even though a tiny amount of amino acid in the scaffold affect the mechanical properties of the scaffold.
Biocompatibility is vital for biomaterials as it ensures safe integration of materials with living cells and tissues, promoting cell growth without causing any cytotoxic effect. In the present study, biocompatibility of scaffolds was evaluated through monoculture of human mesenchymal stem cells, differentiating into bone cells on scaffold for 23 days, followed by sequential culture of human mesenchymal stem cells and breast cancer MCF7 cells for additional 15 days. At first, we evaluated biological response of the cell through cell viability assay, and we found that all the scaffold system show an increase in cell viability over time. However, compared to control, a significant increase in cell viability was observed in aminovaleric and aminopimalic acid modified scaffolds. Further, we performed alizarin rate staining to examine mineralization. Positive alizarin rate staining was observed in all samples, indicating formation of mineralized bone nodules. In monoculture and sequential culture, in both cases, compared to control, a significant higher amount of mineralized extracellular matrix formation was observed with aminovaleric followed by aminopimalic and aminobutyric acid modified scaffolds. Our investigation also suggests that MCF7 cells enhanced mineralization in all the samples. This research highlights the utilization of unnatural amino acids as a powerful tool in tuning the mechanical and biological response of the scaffolds for application in bone tissue engineering and cancer test bed.